Hello everyone. So in here, we, as a Bismarck Battleships group from Marine Engineering 2024, 10 November Institute of Technology, we're gonna explain about the questions in study exercise that Mr. Ede gave us in fluid mechanics lecture.
Assalamualaikum warahmatullahi wabarakatuh. My name is Firin and I'm from Bismarck Battleships team. Today I want to explain about the answer of student report task mechanics fluid number 1. Number 1, what is a buoyant force? So basically, if we ever drop our phone or something down to the bottom of the pool and try to swim downward to get it back, we may need more energy than swimming at the top. Why would this happen? Where the buoyant force takes action. So theoretically, if we stack our books up to 10 times, the lowest book will experience the force because the lowest book has to withstand the mass of the upper books. And that's the analogy. So just as the book states, liquid acts the same way. The lowest point on the liquid means the greatest force acted. So that's why we always get pushed upward when we try to swim downward, because it will make some like layer. If I had some container that's full of water, the container will divide it into many sections. Lower section means higher buoyant force because the lower section needs to withstand the upper liquid mass, just like that. Okay, and B, what is the cause? The cause of buoyant force is make something that goes deep into a liquid experience more force than something on the top of the liquid. So if there is a person who dive into ocean deep down, let's say 10 kilometer, he will withstand a huge amount of force than the person who is swimming at the top of the ocean. Then C, what is the magnitude of buoyant force acting on a submerged body? Volume is theta or something. To answer that question, we may exert some force acting downward on an object that is placed into a container that full of liquid. So if we got an experiment, we need to have some container, water, and then there's an object. The object has to have the higher mass than the liquid density. So the object placed it into water and then we acted some force downward, and then there will be a formula for this. Force buoyant equals to force acting to the up and minus the force acting down, and that is the force of buoyant. And then due to the shape of the object, the buoyant force will act differently depending on the shape of the object, because the formula of force itself is P equals to force divided by A, which A is an area. So the conclusion, the wider the object or shape, if there is a ball and there is a rectangle, the rectangle will have little pressure because of the equation say that P is equal to F divided by A. And the final formula will be F buoyant equal to rho. Rho is the density of the liquid times G times gravity times H. H it means the distance, and minus rho G H bottom minus rho G H tops. And then the last section question is, what's happened if buoyant force from your object is higher than its weight? Based on formula, we assume that the weight of the object is a force acting downward. So we do not exert any other external force to the object. So we let the object.
Hello, my name is Mutiara Hardin, and in this video I will explain for question number 2. For question number 2 is, consider a 13 kg copper triangle and a 13 copper tube submerged in a liquid. If they have the same volume, will the buoyant forces acting on these two bodies be the same or different? Explain the reason. So we have two objects that are copper triangle and copper tube that have the same weight, which is 13 kg. The question said they also have the same volume, which means they occupy the same amount of the space in the liquid. As we know, buoyant force is the upward force from a liquid which happens because of the object pushes aside or displaces some of the liquid. The bigger the volume displaced, the greater the buoyant force. Since both objects have the same volume, they displace the same amount of liquid. That means the buoyant force acting on both is the same, even though their shapes are different.
Hello everyone, my name is Talita Acinta Kirana from Bismarck Battleships. So now I want to explain it question number 3. So the question is, consider a large cubic ice block floating in the seawater. The specific gravities of ice and seawater are 0.92 and 1.025 respectively. If a 10 cm high portion of the ice block extends above the surface of the water, determine the height of the ice block below the surface. Okay, in this problem, we are asked to find the submerged height of a large cubic ice block floating in the seawater. And then we know the specific gravities of ice and seawater, which are 0.92 and 1.025 respectively. And also we are told that 10 centimeters of the ice block extend above the water surface. Okay, first we apply the principle of buoyancy. When an object floats, the weight of the displaced fluid equals the weight of the object. Mathematically, the ratio of the submerged volume to the total volume equals the ratio of the object density to the fluid's density. Since specific gravity is directly proportional to density, we can use specific gravities in the formula. The formula becomes total height minus 10 divided by total height equals to specific gravity of ice divided by specific gravity of seawater, which is 0.92 divided by 1.025. And then we change it, become 1 minus 10 divided by h equals to 0.92 divided by 1.025. And then we move this one to the other side and becomes 10 divided by h equals to 1 minus 0.92 divided by 1.025. And then we solve for h, the total height of the ice block, and find that is approximately 97.66 centimeters. And finally, to find the submerged height, we subtract the portion above water, which is submerged height equals to total height minus 10. And this gives us submerged height equals to 87.66 centimeters. This is the height of the ice block below the surface.
Hello, let me introduce myself. My name is Dhiwa Ihsan. I'm from Bismarck Battleship Group, and I wanna explain about the number 4 equation. For the question is, the pressure difference between an oil pipe and a water pipe is measured by a double fluid manometer as shown in the figure below. For the given fluid heights and specific gravities, calculate the pressure difference delta P equals to PB minus P8. If known, the formula has been given.
For the first one, we get the formula is pH plus the rho of water, HGH the height, and the Hg for the mercury and height of the mercury. And next we got glycerin height and rho of glycerin, and the last we got rho oil and GH gravity height of oil, and that is equal to PB. And as we know that pressure difference is delta P equals to PB minus pH, and then we know that pH is a pressure point A or the oil pipe, and PB is the pressure point B or the water pipe, and the rho is the density of the fluid, and the density of the fluid is including the equation or the formula we see before. It's W for the water, Hg for the mercury, and Gly is glycerin and oil, of course. And we got G, little g is gravitational acceleration, and H is height of fluid column. So I have rearranging the given formula
So we have a equation like this, PB minus PH, and then we put the equation here, same like for the first one, and then the final formula we got this delta P equals to G, and we put the rest of the formula because we don't give specific information about this equation, so we just have the formula into like this.
Hello everyone, so my name is Ismi Zahrotul Jannah. You guys can call it me as Ichi, and I came from Bismarck Battleships group. And right now, I want to explain it about question number 5. So the question is, consider a 1.7 meter tall man standing vertically in the water and completely submerged in a pool. Determine the difference between the pressures acting at the head and attitudes of this man in kPa, or we can call it as kilopascals. To find the pressure difference, we need to consider the difference in depth between the man's head and toes. Since he's standing vertically in water, it means the difference in depth is simply his height. Why we can call it as like that? Because when the man is standing vertically in water, this means his body is perpendicular to the water surface, and in fluid mechanics, depth is measured from the surface of the liquid. So, how we can calculate the pressure difference? And now, I want to show how to solve it. So, the first step how to solve it is identify the relevant variables. So, as we know in the questions before, we have an height of man is 1.7 meters, or we can call it as a difference in depth, and density of water because the man is in pool, so we can call it the water is a fresh water. So density of a fresh water is 1000 kilogram per meter cubic, and the acceleration of gravity is 9.8 meter per second square. So the second one, we need to know the formula for pressure in a fluid. So as we know, the formula of pressure at a certain depth in a fluid is given by pressure is equal density of water, or we can call it as a rho, and then times G, or we can call it as acceleration of gravity, and then times H. And then the third step is calculate the pressure difference, or we can call it as delta P. So, as we know, the pressure at the toes, it will be greater than the pressure at the head because the toes are at greater depth. So, the pressure difference is delta P equals P toes minus P head. Because of this formula, we can have the formula is delta P is equals rho GH toes minus rho GH in head. And then we can make a simplify from this formula. It's gonna be delta P equals rho G and H2 minus H hat. And we can say it H2 minus H hat is equal to the height of the man. And then we can have the formula is delta P is equals rho GH. And then the first step is substitute all the values and start to calculate it. So because from the previous step we have a formula is delta P equals rho times G times H, we can substitute the value that we have from the question. It's gonna be delta P equals 1000 times 9.8 times 1.7, and it's gonna be 16,660 PA. And then the last step is convert Pascal or PA to kilopascals. We need to convert it because in the questions it's need us to determine difference pressure in a kPa or kilopascal. So as we know, 1 kPa is equals 1000 PA. So it's gonna be delta P is equal 16,660 is divided by 1000, and it's gonna be kPa. And then the last value, it's gonna be 16.66, or we can call it 16.7 kPa.
Question for number 6 is a gas is contained in a vertical, frictionless piston cylinder device. The piston has a mass of 4 kg and a cross-sectional area of 35 cm square. A compressed spring above the piston exerts a force on a range from 0 until 500 Newton with 1 Newton increments on the piston. If the atmospheric pressure is 95 kilopascal, Determine the pressure inside the cylinder. From the question, we got mass of the piston, which is 4 kilogram. We got cross-sectional area of piston, which is 35 centimeter square, and we convert to meter square, which is divided by 1000. So we got 0.0035 meter square. Then we got spring force from 0 to 500 Newton in 1 Newton increments. Then we got atmospheric pressure, which is 95 kilopascal. And for gravitational acceleration, we use 9.81 meter per square. Okay, so for number 6, we use axle. For the first column is filled by spring force from 0 until 500 Newton, and for the second column is filled by pressure inside with kilopascal units. We got this number are from this formula. I'll put it here, and it divided by 1000 because we want to convert from Pascal to kilopascal. That's all from me. Thank you.
Hi, I'm Talita again, and now I want to explain about question number 7. So the question is, if a diver dives at 30 meters below the free surface of the sea, assume a barometric pressure of 101 kilopascal and a specific gravity of 1.03 for seawater. Please write your engineering judgment on whether the diver will die due to the pressure or not. Explain your judgment or the reason. In this question, we are asked to determine if a diver at a depth of 30 meters below the sea surface will die due to the pressure. First, we know the barometric pressure at the surface is 101 kilopascals. And for the specific gravity of seawater is given as 1.03. Then we calculate the pressure of 30 meters depth using the hydrostatic pressure formula, which is pressure equals to atmospheric pressure plus hydrostatic pressure. Now we calculate the hydrostatic pressure, which is P times G times H. And then we substitute the point of specific gravity times height. Then we got 309 kilopascal. And then we adding the atmospheric pressure, and it becomes 101 plus 309, and it equals 410 kilopascal. This total pressure is about 4 times at atmospheric pressure. From my perspective, a trained diver can typically survive underwater pressure up to 4 or 5 atmospheres with proper equipment like scuba tanks. Therefore, at 30 meters, a healthy equipped diver will not die due to the pressure alone. However, without proper training or equipment, the diver could experience conditions like nitrogen narcosis, but that purely due to the pressure at 30 meters is unlikely.
Hello, my name is Muhammad Dhiwa Ihsan, and today I will explain about the number 8 equation. For the question is, give your judgment and opinion about on the stability of the ship, as A is submarine and B is floating body or a ship or main vessel, whose center of gravity is above the center of buoyancy. And here's my explanation. So the first one is buoyancy force basics. Include the buoyancy force basic, and so like we have the basic formula of buoyancy as rho fluid times G times V, density times gravity and times volume. If FB more than weight, the object will float on the surface. The second one is stability rules. For the submarine stability rules, the stable one is a center of gravity below the center of buoyancy. If we'll make a tilting crease, a restoring force like a pendulum, and unstable G above B, submarine will flip down or spin. To fix it, we have to add ballast weight to low keep down the G. So the B the answer of the B, we have the floating body of a ship. For the floating body of the ship, the meta center is above the G. We have to put it above the G, and shift will make it right itself when it's still. And for unstable, because the G is too high or too close with M of the floating body. That's for my explanation. Thank you very much.
Hello, this is Ichi again, and right now I want to solve the question number 9. So the question is, the hull of a boat has a volume of 36 meter cubic, and the total mass of the boat when empty is 1000 kilogram. Determine how much load this boat can carry without sinking, and the first one is in lake, and the second one is in seawater with a specific gravity of 1.025. So basically, to solve these questions, the key is all about Archimedes principles, which states that the buoyant force on an object submerged in a fluid is equal to the weight of the fluid displaced by the object. So, based what I explained before, here's how to solve it. How to solve it? The first one is we need to identify the relevant variables. And as we know, volume of the hull is 36 meter cubic, and the mass of the boat when the boat is empty, it's gonna be the mass of boat itself, and then the mass of boat is 1000 kilogram. A density of water in a fresh water is 1000 kilogram per meter cubic, and density of water in a seawater, it's gonna be 1025 kilogram per meter cubic. And then in here, we have an acceleration of gravity is 9.8 meter per second square. So the first step is we need to find the maximum buoyant force in the lake. As we know how to find the buoyant force, the formula is gonna be buoyant force is equal rho from the water times of the volume and then times of acceleration of gravity. In here we can substitute all the value that we have from the questions, and it's gonna be buoyant force is equals 1000 kilogram per meter cubic times 36 meter cubic times 9.8 meter per second square, and it's gonna be 352,800 newtons. So the second step is we need to find the weight of the empty boat, or we can call it as W boat. Formula when we need to find weight is W is equals mass times G. And then we can say it is W boat is equals mass of boat itself is times gravity. Here we can substitute all the values that we have is into the formula, and then it will be W of boat is equals 1000 kilogram times 9.8 meter per second square, and it's gonna be 9800 newtons. The third step is calculate the maximum total weight the boat can support. So, for the boat to float without sinking, the buoyant force must be equals to the total weight of the boat and its load. So we can write the formula like this way. So the buoyant force is equals W boat plus W of load. And then, as we know before, we have a buoyant force is 355,800 newtons equals to the W boat that we already calculated before is 9,800 newtons plus W of load, and it's gonna be 343,000 newtons. And the fourth step is convert the weight of the load to mass of the load. As we know, the formula to find the weight is weight load is times mass of load itself times G. That's why when we need to find the mass of load formula, it can be like this, and then we can substitute all the value that we have, and the mass of load it's gonna be 35,000 kilogram. So from these solutions, we can say the amount of load that can be carried by the boat is 35,000 kilogram in lake without sinking. And then we need to solve the same thing, but this is in a seawater. So before I start to the first step, as we know, at the questions, we have a specific gravity of seawater is 1.025. Why the seawater is gonna be 1025 kilogram per meter cubic? Because the density of water or fresh water is 1000 kilogram per meter cubic. So that's why if we need to
find the density of seawater, we can calculate it as 1.025 is times 1000 kilogram per meter cubic, and then we have 1025 kilogram per meter cubic. I'm gonna start to explain the steps. So the first step is we need to find the maximum buoyant force in the seawater. As we know, the formula is like this, and then we can substitute all the value is 1025 kilogram per meter cubic times 36 meter times again with 9.8 meter per second square. And then we have it, the buoyant force in the seawater is 361,800 newtons. And for the second step is calculate the maximum total weight of the boat can support. For the boat to float without sinking, the buoyant force must be equal to the total weight of the boat itself and the total weight of the load that must boat carry. And it's gonna be 352,000 newtons. And then the third step is convert the weight of the load to the mass of load. And then as we know, when we need to find the weight, it's gonna be W is equals M times G. And then when we need to find the mass of the something, it's gonna be like this. So we just need to substitute all the value that we have, and it's gonna be like this. And here from these solutions, you can say the amount of load that can be carried by the boat is 35,918.37 kilogram in seawater without sinking.
So, from these questions, we can get a conclusion from two different problems, and the conclusion is the boat can carry more stuff in the oceans than in lake. This is happened because the ocean's water, it has more density of water than in lake, or we can call it as a density in a fresh water. Because the water in a seawater is more denser, so it's gonna push us up on the boat more strongly. The extra push allows the boat to hold more weight without sinking.
Again, my name is Ahmad Mustaghfirin Amin. I'm from Bismarck Battleships team, and then here I will explain how do we get the answer from question number 10. In question number 10, there is an engineering study case easy version. I will make it into some section. There is introduction, artist company, the babadong, the vessel, the issue, and our strategy, and then the last is conclusion. In the introduction, I used to explain what is the main case this problem, what is the main issue, what's the subject, what's the object, and then where do we as a marine engineering take place in this case. Then in the artist company section, explain and give our idea to the company to overcome this problem. And then the second one is the babadong. Babadong is the second company, so we do like before artist company, we also break down this company and then try to understand the issue on this company. And then the vessel, so these two companies are working together to make some vessel. This is client and producer, and then they try to make a vessel with special requirement. In this section, we make this illustration to make us easier to analyze. And then the next section is the issue. The issue, we break down what is the issue on these two company from the bottom to the top. And then the next is our strategy. And here basically in the most important section in this task, in this report, we gave our idea and our strategy to solve this case. And then the last section is conclusion. So in the conclusion, we try to conclude from the beginning to the end of the report. What is going to be, how do we solve this case. That's all for me, and thank you.